Okay, so today we'll go on with like yesterday, and today I will go more into the details of some experiments I've been involved recently and which can be used, that have been used to set relevant upper bounds on the parameter space of collapse model, particular CSL models, just by doing a direct measurement of fundamental fluctuation of mechanical resonators. I have some short introduction about the measurement problem, the collapse model, but I guess you have already had a good lectures on this, so I will go fast on this. And but just to refresh the concept, so the measurement problem is a contradiction between the two fundamental dynamics which are postulated by standard quantum mechanics, the standard evolution, which is linear, and so the quantum superposition principle holding all the time, and on the other hand, the measurement process requires breaking the collapse of the wave function, which involves breaking linearity. So these two are not, with this definition, these two dynamics are not consistent with each other, and quantum mechanics is not does not clearly define what is actually when actually a system is qualified to be a measurement system. That you have to apply this, and well, you can you know, there are many possible ways out of this problem, which are mainly interpretation of the theory. The coherence solves part of the problem, but not completely. And we are interested in the idea of the collapse model, which is actually both dynamics exist at the same time in fundamental level, so that you have actually, you are modifying the theory. You are modifying the theory so that you have actually experimental predictions which are different. This is the good point from the point of view of experimentalist, that this option is, at least in principle, it can be experimentally tested. And in a spontaneous collapse model, you assume that basically quantum mechanics is some microscopic limit of a more general theory in which you have also the collapse inside the dynamic, the real dynamics of the system. And in particular, you have some kind of dynamical reduction which takes place all the time, which is completely negligible for microscopic systems, for atoms, for instance. The collapse rate will be like one every time of the universe, age of the universe, but then you have some amplification mechanisms that for larger objects you can have a collapse, which happens on a realistic, fast time scale. And the other nice thing of the collapse model is that, of course, the measurement problem is solved. You don't have any more an ambiguity in the definition of measurement. Measurement is just a situation in which you have some macroscopic apparatus which is interacting with some quantum system. Then when the two are entangled, you have a collapse, because the whole system is macroscopic. I will focus on this CSL model, which we have already seen. So it's just a stochastic modification of the quantum evolution. And here in this model, you have two fundamental parameters. This is the most studied or the most general model in which you have actually two fundamental phenomenological parameters. One is RC, which is the correlation length of the noise of this sort of collapse field, which you can think is some noise field which is everywhere, and there's a subcorrelation length. And this is the collapse rate, so the strength of this collapse, which is, according to the original proposal of Girardi, Rimini, Weber, should be in the order of 10 to minus 16, which is what is required, would be enough to collapse macroscopic superposition at human scales, right? While according to Adler, this collapse rate could be much higher, because it requires only the columns to be efficient at some mesoscopic scale. Okay, this is the field. So, as I said, the nice thing is that this model can be tested. So we can, in principle, test the prediction of quantum mechanics, standard quantum mechanics with respect to collapse model. And, well, the most direct way will be, of course, to do matter wave interferometry. The most fascinating way, of course, is to try to create quantum superposition of macroscopic objects. You have also seen that these experiments are extremely challenging. But you have also this other way, this so-called non-interferometric methods, which are comes out because all these models, like CSL, to be consistent, require that there is some kind of violation of energy conservation. So there is some kind of noise which shakes any kind of mechanical system. So you can use a mechanical system to mechanical resonator to look at the fundamental fluctuation of this resonator and try to figure out if there is some fundamental noise acting on this. Another method is looking for instance, spontaneous emission of free electrons in solid state system, which also sets significant bounds. Okay, so I will go into the mechanical option, of course. So the idea is that if you have very simple, the experiments are extremely simple. You have a mechanical resonator, and if you have this fundamental noise due to collapse field, you will, well, suppose that the system is completely isolated, there is no thermal bath. You will have just that the energy of the system will increase with time, with proportional to this the spectral density of this force. Of course, in a real system, you don't have only this. You have at least other source of noise in general, but at least you have the thermal noise because you have some environment. And okay, there is something wrong here, but not a problem. If you have this dissipation, you have thermal noise. You can calculate that. Some formatting problem, but you can understand here. It turns out that the mean energy of the system is given by the thermal energy, K Boltzmann T, at equilibrium, plus a term which comes from the CSL field. So basically, the effect of if you're just monitoring the mean energy of the system, the effect of the CSL would be just a violation of the equipartition. You should see some excess noise above the equipartition thermal energy. So the CSL effect can be actually calculated explicitly, and for a mechanical resonator of a given geometry and given material. At least for what it has been done so far, it's possible to calculate the effect exactly for the rigid motion of a system. So you have like a sphere trapped in an harmonic potential. You can calculate exactly what is the CSL effect, CSL heating of the mechanical resonator as function of the parameters of the model and the parameters of the system. This is the formula, full formula that gives this parameter eta, which, so the increase of temperature you get is proportional to this parameter eta, which is sort of diffusion constant. It's proportional to this force noise of the CSL field. You have also some parameter of the mechanical resonator here, the quality factor and the frequency. This comes out because you are actually measuring your increase of temperature compared to the thermal noise. So these are parameters that come to the thermal noise. And so for a sphere, for instance, you can calculate exactly this integral. This integral, you see, you have a Gaussian here, which is essentially a Gaussian with width of RC. So essentially, this is the correlation length of the noise. And then you have this term which is proportional to the derivative of the density with respect to the distance. So this is no zero when you are on the surface, actually, in a homogeneous body. This turns out to be somehow an integral on the surface. So sort of surface noise, as it was some kind of gas particle that hits the surface. But it's just an analogy. So that in the case of a sphere, this is the formula. I'm not going into the detail, but if you plot the increase of temperature function of the size of the sphere, normalizing the RC, typical length, the length of the model, then you see that there is a maximum. So the effect, if monitoring this kind of effect, what you have to do is to use an object which has the same size of the RC. This is the simple recipe. I don't know if you can see anything here. Anyway, well, you can also write this increase of energy as a product of these two quantities. This depends only on the CSL noise, and this is just the parameters of the mechanical system. This is essentially the force noise of the system. So if you want to maximize the signal, let's say signal to noise ratio, actually it's noise to noise ratio, but you want to minimize the noise, and it's exactly coming here with your high quality factor. So decouple your system from the thermal buffer in the environment. And low frequency, these are the two parameters we have seen yesterday. You have to optimize. If you want to measure very low, very small forces. And then you have the mass. Then, okay, I've already said that you want the size of to be comparable with the length of the model. And then you want high density, because in this eta parameter there is a high, there is a square of the density here. So it's important, if you want to maximize the effect, you want to maximize the number of the density of the material, because the collapse field couples with the number of the mass, essentially, the number of nucleons. So what are the possible approaches you can take to investigate this effect? So the thing I will analyze in more detail is this. So mesoscopic systems, mechanical system, nanomechanical resonator which have a typical size comparable with RC in the order of 10 to minus 7, 10 to minus 6 meters, which is what the theorists say the most reasonable value for this parameter. Although this is a free parameter. A priori, we don't know exactly, the theory does not tell us what this parameter is, but there are some arguments that suggest that it should be, if CSL exists, it should be in this range. Then mechanical systems, mesoscopic mechanical systems can be easily cooled to cryogenic temperature and below, up to 10 millikelvin, as I will show. And this is a good advantage. The disadvantage, well, it's not easy to work at very low frequency, because typically nanomechanical resonator have high frequency. And I will show experiments in the lowest range, in the kilohertz region. So I will consider systems which are optimized at kilohertz frequency, which is the one that gives the best result for this kind of investigation. Next, I will consider, so you want to decrease the thermal noise, essentially. That's why you go to low frequency. So the force noise improves by going to low frequency. Yeah, the Q over omega comes out, it's essentially due to the thermal noise. what you want to increase this heating. This is your signal, in a sense. And you maximize this by okay. Okay, then I consider a macroscopic mechanical system for precision measurement, in particular gravitational wave detectors here. The big advantage of this system is that they have been designed to work at a very low frequency, and it's very difficult to work at a very low frequency, but if you want to detect the gravitational waves, you have to do something very difficult. And actually, there are systems that are optimized at milliards frequency. So you get something like 3 or 6 orders of magnitude here. But this is compensated by the fact that usually you work at temperature and the size is not the optimum. Because you are, compared to the RC of 10 to minus 7 to minus 6, if you take, for instance, the test mass of LIGO is like this meter size. So you lose other orders of magnitude. So in the end, all the things compensate. There is another approach which is looking at ultra-cold atoms. In this case, the advantage is that you have extremely low temperature, like in the nanokelvin. And in this case, the effect of a CSL is very tiny because the size is very suboptimal. The size of nuclei. So now I start with this option, and so I consider mechanical system optimized for kilohertz frequencies. I start just introducing this atomic force microscopy. It's a very useful technology that is used nowadays in many applications. And as a required the development of very nice devices. Basically, just to introduce that this technique is you are actually sweeping a mechanical resonator, a cantilever, over a surface of a sample, and here you have a tip, which is atomically sharped. So basically, you have a single atom and the end of the tip. So when you scan over your sample, you can probe the force between this atom and the surface, and you can actually get from the force you get when you scan over the sample, you can get information about the surface of the sample with atomic resolution. So you can really see single atoms with the tip. This is a nice application of mechanical systems. Next, what I want to introduce is that people have tried to figure out whether it's possible to use some kind of similar technology to measure actually to do something like that with single atoms resolution, but in which you can see also below the surface. So do some kind of three-dimensional imaging of some nano object. And if this were possible, this would be would open new horizon in, for instance, in biological sciences, because you will be able actually to reconstruct the shape, the position of atoms inside very complex systems. Something that people would like to have, but doesn't exist. But people have tried to figure out if it's possible to use some kind of mechanical technology. What? Yeah, it's possible to do, but the point is to do a three-dimensional, at a single atom. What? Yeah. But, well, no, that's, I mean, to do it on a general system. Yeah, but the point is to achieve a single atom. But well, now it's just to show you that there is a technology under development which is based on this, that has required the development of a very sensitive mechanical system, and has this goal. You mean which kind of technology are you? Yeah, but I don't think you can go to detect single the position of single atoms. Or you can get not all of the atoms, maybe a single. Yeah, that. Yes, that you can do. But there is not a general technique that can be applied to any kind of structure. But well, this technology that has been proposed is based on combining mechanical technology with MRI. You know, magnetic resonance imaging is a technology which allows you to image your, for instance, the brain, or in this case, or part of the body. It's three-dimensional. It's based on the fact that you are actually applying, so you know, magnetic resonance, you apply a static magnetic field and spins. The levels of spins becomes split by the magnetic field, and you have energy, transition energy, which is proportional to the magnetic field. And you can drive this transition using RF signal. So now if you apply a gradient inside your sample, you only the spins that are in where the field is exactly matched to the resonance frequency will be resonance. So you can get the signal from signal by sweeping the field. You can get signal from different parts of your sample, your scan. And then this is why this is three-dimensional. You're really getting signal from different parts of your sample. But this technology has very poor resolution because you need a very large amount of spins to get signal. So people have invented this technology which combines the two approaches. So you have basically a cantilever in which you put a magnetic particle. It generates a very strong magnetic field, very strong gradient with a ferromagnetic particle. Then you bring it close to a sample, and then you have a force between the two, between this magnet and all the spins inside your sample. And you want to measure this force, this very tiny force, like typical forces are in the order of 10 to minus 18 Newton for electron spin, or 10 to minus 20 Newton for nuclear spin. Extremely small. But what is the advantage? The advantage is that the gradient can be very high here, because they are nano objects, so the field generated by this guy drops very quickly with the distance. A very strong gradient, so the resolution, when you think in terms of the spatial resolution is very high, because this spin will be in resonance, but the next spin will be no more in resonance because the field is distributed very quickly. So you have a very high resolution, but the signal does not drop to zero when you reduce the number of spins. The force, when you increase the gradient, you increase the resolution, but you also increase the force, because the force between a gradient and a spin is proportional to the gradient. But that's just a general idea. I don't want to go too much into detail, but I want to show that this technology has been demonstrated, actually, and these are some milestones, especially in the group of IBM, in the Ruger group in California. They've been able to demonstrate this technology using very nice cantilevers. I will describe now, optically monitored. Then they have a sample somewhere on the cantilever, and here you have a strong magnet. And then they apply magnetic resonance. So it is a very complicated experiment, but they demonstrated this is an MRI scan of a virus, a nanoscale with nanometer resolution. That's the density of spin at nanometer resolution. And with the same device, they have been able to couple to a single spin. So the motion of the cantilever has been coupled to a single spin. So in principle, you can also use a mechanical system as in quantum technologies to do some kind of readout or actually manipulation of single qubit. Okay, but I go back now to the original motivation of this presentation, is that this technology has required the development of cantilevers which are very special, because they are designed to detect very small forces, like, as I said, like the order of 10 to minus 18 or even 10 to minus 20 Newton. No, that's not achieved yet. That will be required for single nuclear speed. And So, how this is achieved? By fabricating very high aspect ratio devices. Basically, these cantilever are very long and thin, so like 100 nanometers over a length of here there is an error. This is 100 micron. There is an error here, but these cantilever are extremely floppy. So basically, they are very sensitive to forces because they are extremely floppy. Actually, you have to be very careful because you have a situation in which this cantilever actually can even fold. They are so floppy that they can actually fold completely and without breaking. They are made of silicon, single crystalline silicon cantilever. Typical frequency are in the kilohertz. And as we said yesterday, if you want to get the lowest possible force noise, you want IQ, low temperature, and low K. So when a few years ago, I was a postdoc in Leiden in the group of Oosterkamp. The idea was actually to develop this technology, but sorry, I didn't explain. This experiment was performed at 1 K, cryogenic temperature. And they were not able to go below this temperature because it turns out that as soon as you shine a laser here to a detector position, this guy gets heated. So they have tried to, just because of absorption of photons from the laser. These people have tried to cool to millikelvin, but they've seen that basically as soon as they shine a laser, to measure it, this gets just stuck to something like 1 Kelvin or so. So basically, you are cooling everything around the system, but the only thing that you want to cool does not cool, so it doesn't help. So what we wanted to do here, try to do something similar, but trying to really achieve this very low temperature with the temperature of the cantilever, not just the surrounding. And what we've done then was, well, the cantilever is very similar. Here it looks like a wire, but it's just because it's seen from the side. So this is a rectangular springboard type cantilever. Here you attach actually a sphere with a magnet. Now I will show why we do that. This is the way we attach this sphere to the cantilever. This stuff on this on the right is a bunch of magnetic particles. This is some neodymium iron boron magnet. Is most used magnetic material for ferromagnetic application. It's hard. It's just that this kind of magnet is easy to once you magnetize it, it's very difficult to demagnetize. Very stable magnetism. So basically, here we bring this is an electron microscope. We bring this cantilever. This is the tip of the cantilever. Cantilever sticking out. We bring this close to the stuff here until this part. We approach the tip of the cantilever to one of these spheres. Then we glue it using some electron beam deposition. Then you retract, and you have this particle attached to that. So why do we do this complicated stuff? Because we came up with this idea. So that, as I said, we want to reduce the temperature of the system. So we want some different technology to detect the motion. And you came up with the SQUID detection, which is something like that in our this initial experiment. This is the scheme. So the cantilever with the magnetic particle here, and we approach this cantilever to a coil. This is a detection coil. So when this magnet moves here, it couples some magnetic field into this coil, so that you can detect this field, and this is generates a current into this superconducting circuit, and this current couples flux into this sensor, which is a SQUID. We have already seen yesterday something about SQUIDs. Now maybe I try to explain what exactly is a SQUID. But the idea here is that essentially you are getting a signal here, flux, proportional to the displacement of the transmission. So you have basically a linear measurement of the displacement. And in this case, we achieve the displacement sensitivity, which is not fantastic, but for this experiment was quite actually enough for us to detect easily the thermal noise of the So a SQUID, well, I have some slides on the SQUID, but I don't know if you have any idea of how it works. Anybody has ever learned about Josephson junctions? Nothing. So maybe I have to explain what a Josephson junction is. So basically, a SQUID is a superconducting loop, which is interrupted by two Josephson junctions, overdamped. So a Josephson junction is it's a layer of a thin layer of insulator between two superconductors. So classically, this would be just an insulating barrier. But since the thickness of this layer is comparable or smaller than the coherence length of the Cooper pairs in the superconductors, it happens that you can have macroscopic tunneling, quantum tunneling, coherent quantum tunneling of Cooper pairs from here to here, which is called Josephson effect. It was Josephson got the Nobel Prize for this by predicting this effect before it was discovered, actually. And what happens is that the superconductor can be described by a sort of order parameter, which is basically a macroscopic wavefunction. So you have a macroscopic phase and an amplitude, which is proportional to the density of Cooper pairs. And what you have that this phase is defined on the superconductor, depending on the position. And you have, when you have a Josephson junction, you have the current through the Josephson junction is related to the sign of delta, where delta is the difference of the phase between the two sides of the superconductor. And you have a voltage, which is something like this. It's proportional to the derivative, well, maybe there is some 2 pi somewhere, but it doesn't matter. So the voltage is proportional to the derivative of the phase. So if you have a voltage here across between the two, it means that the phase must rotate. While if you have a supercurrent, you have just a static phase, and then you have no voltage. So you have a supercurrent. So SQUID is essentially two Josephson junctions in parallel. EBF more or less has a single Josephson junction where the flux somehow modifies the critical current. So sorry, this parameter is the critical current, is the maximum current, supercurrent that the junction can sustain. And it happens is that if you force a current larger than the critical current in here, for instance, you can put a resistance here in parallel. or otherwise you can just have some incoherent tunneling. Then you will have some voltage appearing because if you exceed the critical current here, so larger than type 0, you exceed the critical current, you have a voltage, and then it means that the phase has to rotate. This rotation is called Josephson oscillation. It means that there is really a current which is, in the case of the SQUID, which flows in the loop at high frequency. Typical oscillation frequency are in the gigahertz frequency. And you have a voltage appearing. But the important part is that if you work in the voltage state, where the current is larger than the critical current, you have these oscillations in which the voltage is directly related with the frequency of this oscillation. That's the nice thing, because you are relating directly frequency to voltage. People that do metrology are very interested in this thing because of this property. You can define actually the unit of voltage through this relation. And but in the case of the SQUID, what is interesting is that the following: if you apply a flux here, you are effectively changing the critical current, and you are actually changing this frequency. So this happens to be, well, the best analog I can do. It's a nonlinear device. It's very difficult to explain exactly how it works. But since you have learned about optomechanics here, the best analog I can do is that this is here as a sort of cavity, in which, as in a cavity, you have the displacement modulates the frequency of the cavity. In this case, a flux, external flux, is changing the frequency of these oscillations. This Josephson oscillation, which is related to voltage, and you can directly measure this voltage. And the dependence is periodic with the period given by this quantity, which is actually a fundamental constant, h divided by 2 known as flux quantity. So in practice, to conclude, you have a flux. If you apply a flux, you have this periodic dependence of the voltage to the flux, which is comparable to the the amplitude of the phase of the mechanical cavity is function of the changing of the displacement of your mechanical system. Okay, so this object can work as a measurement device, which is close to the Heisenberg limit. It's not at the Heisenberg limit because to operate this device, you need some resistance here, and you have some thermal noise, and this happens to be a fundamental limit. You cannot go really. You can go close to the Heisenberg limit, but not really at the Heisenberg limit, so far at least. Quantum description of this object is very complicated. It's not like a mechanical system because it's very nonlinear, this system. Some people have tried to calculate the response, and it turns out to be a very nonlinear parametric amplifier. Okay, go back to the experiment. So I don't know if you have understood more or less how it works, but in practice is something that measures flux, magnetic flux, and converts it into an output voltage. We do our experiment in a dilution refrigerator. I already explained yesterday. So go back to the experiment. This is the scheme. So that using a SQUID, we measure the displacement of this cantilever, and this is what we see. So this is the signal, the Lorentzian peak, which are basically the fluctuation of thermal fluctuation of this cantilever at 2 different temperatures. This noise is the noise floor of the SQUID, and this is the mechanical noise. You see that if you cool to 1 Kelvin to 11 millikelvin, you see that the noise drops. So now it means that the system works for the thing we were aiming for, because we are actually able to cool the effective temperature of this object, so reduce the thermal fluctuation. Now the area under the peak is the energy. It's proportional to the resonance time. So in this particular experiment, we also have devised the method to calibrate, perform an absolute calibration of this energy. It is basically based on the fluctuation dissipation theorem that I showed yesterday. You remember the idea that if you can measure the response of the system to an external force, you can get information that allows you to predict the thermal noise. This is what we do here. We send the signals to this auxiliary calibration transformer. So you can inject a flux here. We drive a current, and this drives the cantilever. You can measure very accurately this transfer function, and we do actually here. This is the response. From this response, we get this parameter here, which is actually what you need to convert the output voltage you measure, so the area actually of these peaks, into the effective temperature. This is somehow different from what I have seen yesterday with the fluctuation dissipation theory, but exactly the same thing. It's just that expressed in a different way. So you measure the response, and from the response, in amplitude phase, you can predict the thermal. And this is what we get once we calibrate. So at a different temperature, we sweep the temperature, then we let the system thermalize for some time, and then we measure the noise. We do it at many temperatures, and what we get is this. So this is the area under the peak, normalized in a mean energy, or if you want, in a temperature. This is the effective temperature of the noise. This is the temperature which you measure using the thermometer. You have a thermometer, standard thermometer, attached to the setup. And this is exactly what you expect. Just a trivial linear behavior with a slope equal to 1, so the simplest thing you can imagine. But this is just the equipartition. We have just demonstrated that, checked in our system that the equipartition theorem works fine. Except here you have some point that deviates. This is due to some kind of saturation. So somehow you cool in this region, and the cantilever temperature follows the external temperature, the bath temperature. But once you reach this point, there is somehow decoupling, the thermal decoupling, which is very typical at very low temperature, because the thermal conductivities of any material drop to 0 when you go very low temperature, especially for insulators. So this cantilever is an insulator, and the heat capacity drops as the cube of the temperature. Yeah, unfortunately, I cannot see very well, but so I repeat. So at each temperature, so here is the temperature measured by a thermometer, and here is the area of the peak converted into temperature, calibrating into temperature. So we measure the area, using the calibration, we transform into an effective temperature. So this is the noise as a function of what we see is that essentially the energy of the mechanical mode, this single degree of freedom, is kT. This? Yeah, I just said that this is a saturation in the sense that basically the temperature, you have, but there must be some kind of input power, which we don't know what is. And well, that's very simple to. You can think of the cantilever as a system that is at the temperature T, and this, you have some thermal bath, and then you have some thermal resistance here, and suppose that you have some input power here. And if this resistance is very small, you will not see any difference. And we are here. But if this resistance changes very quickly with temperature, in fact, these are typically proportional to T minus 3. So when you cool down, it becomes very high. this may be just, if you have this cantilever, which is long and thin, and you have some power dissipation, which we don't know where it's coming, but it will come, for instance, from the squid. Then you might have a gradient here. So the temperature along the cantilever could be zero, you know, but could be somehow higher. And if you go to sufficiently low temperature, this resistance at some point will show up. And this gradient is will become significant. Is it clear? There is always some power that enters the system from the readout, actually, some microwave photons, something looking at it. And it's practically impossible to do a complete shielding. So at some point, if you go to sufficiently low temperature, you will see some decoupling. Even if any system decouples at some point, people that do experiments with microkelvin, actually they can do experiments only using copper and a very high conductivity material. But it's basically impossible to cool an insulator efficiently to such temperature because you have really to be careful to any kind of heat leak. Even cosmic rays or anything like that will heat up your system and you will not be able to. Okay, well, in this case, I can go on. This is the minimum force on RVF measure was for the 10 to minus 19 Newton, which was at the time was actually the lowest force noise ever measured. Now, go back to the CSL. So, if you have a CSL effect in the data, how would it appear? It will show up as an intercept in this plot. Because there is you would have a delta T, an increase of temperature, which is independent of the temperature of the system because it's some fundamental effect. So that you would expect a linear behavior because there's a thermal noise. You must see this, but you would see some intercept in the data. We don't see this, so because this scales to 0 actually. But from the error bar, we get something like this. The delta T cannot be larger than 2.5 millikelvin. If there is some effect, it cannot be larger than 2.5 millikelvin. And from this data, we can actually connect to the CSL parameters. Because now we know that given the geometry and the material of this object, we can calculate, and given the parameters of the model, we can calculate how much is the increase of temperature we expect from this system. Actually, there are some problems here. Well, it was not so trivial to calculate it because this is a composite object, and the people that do CSL calculation have done calculation only for rigid body motion and simple geometries, while this is actually a bending motion, is something more complicated. So what we have actually found with Angelo Bassi and the group, we have tried to estimate the CSL heating in this case, and it turns out that the sphere on the top of the end of the cantilever is actually given the strongest contribution because the density is higher, and it gives by far the strongest contribution. So, in first approximation, this is like a nanoparticle trapped in a harmonic potential from the point of view of CSL. Actually, the cantilever gives a small effect, but it's significant, but not large. And it's more or less like having, since this is a bending motion, only the effective part that moves actually gives a contribution. So it's more or less like having a shorter cantilever moving rigidly. That's more or less the conclusion of our analysis. Anyway, you can calculate this increase of temperature. This is using the Ghirardi-Rimini-Weber values, which are the most conservative value of 10 to minus 17 Earth of lambda. What you expect is this, depending on the RC of the model. This is the contribution from the sphere, this is from the cantilever. So basically the sphere gives the largest contribution. And the effective temperature we would expect would be 10 to minus 10 Kelvin. Okay? This is the temperature you should be able to reach if you want to, using this system to fully test the collapse model down to the gradually milliweber, which is quite impossible. However, what we could do using this data and combining with this maximum temperature, increase of temperature, we can get an upper limit. So this is the parameter space of CSL, lambda RC. And this is this red line corresponds to this increase of temperature of 2.5 millikelvin, which we have established to be the maximum allowed by the experiment. So all this region above this is excluded by the experiment. If you had some CSL somewhere here, we would have seen. Okay, how does it compare with other experiments? Well, or with theoretical prediction? Well, you can see here, basically here you have the matter wave stuff, more or less here. This is the lower bound from the gradually milliweber. These are the predictions from Adler. So we are more or less overlapping the Adler prediction. And this is the X-ray spontaneous emission. So this experiment does a bit better than X-ray here, but at 10 to minus 7, which is the standard scale, we are here quite far, as you can see. Actually, in the X-ray, well, the allowed is below, the excluded is above. In both cases. But X-ray, well, there's some consideration that to do that. In the case of X-ray, somebody claims that these limits are not so strong because, well, you can assume that just if this collapse noise has some cutoff, then before the frequency of X-ray, you will not see anything with X-ray because X-ray emission actually probes the collapse field at a frequency of 10 to the 18 Hertz or so. But if you have a cutoff at 10 to the 10, you would not see anything. Yeah, I think so. Cooled atoms. I can show later, but I have a slide, but I think we are more or less here, a bit higher than the Cantilever. Some 10 to minus 8. At least in the experiment we have analyzed with Angelo. I don't know if there are other experiments more which can do better now. But yeah, at the moment, at this scale, X-ray is by far the strongest bound. Just with this consideration that it might be, it's easy to evade this bound by little changing of the model. What I want to say is the Adler prediction actually were done assuming that the time scale of the process was in the order of second or millisecond. And this is more or less the time scale of our experiment. We are probably at 1 kilohertz, so a few kilohertz. So our bound compares more or less with the same time scale. It's a direct probe of the Adler prediction. Okay, now more recently, well, 1 year ago when we came up with this paper, so actually we did this experiment several years ago. Only 1 year ago, I realized just talking with Andrew that this experiment could be somehow relevant for this field. I didn't know anything about collapse model before, basically. And after we did this paper, actually during the paper, because this here actually the paper, we have tried to discussing also with Oosterkamp, and we are trying to figure out where you can go with this method. just by applying this simple method. And it turns out that you can improve significantly this bound by the parameters. The parameter which is more important here is the heat. The quality factor of this experiment was not very good, not 10 to the 5. But it's possible, as we've seen yesterday, it's possible to achieve something like 10 to the 7 using diamond cantilever, or I also seen that you can achieve this also just with silicon cantilever, as I will show now. Or, well, you can use heavier material, you can do other things probably. And we have come up with this possible improvement which you can achieve with existing technology, not with just assuming that we can optimize all the parameters at the best you can do today. And then recently I actually did something in this direction because I found that it's very easy actually to have a cantilever with a very high quality factor, and I found it that just conventional atomic force microscopy cantilever cooled to very low temperature actually, this is the measurement I showed yesterday, which you see that the quality factor improves very sharply when you go to very low temperature, at least in this system. And I could achieve actually 10 to the 7, which is 2 orders of magnitude better than the previous experiment. The difference is that this system is much heavier, is thicker, 2 microns instead of 100 nanometers. It is much more rigid. So you gain something in the quality factor, but you lose something because you have something that is more rigid. But I did some estimation, and it turns out that this can do somehow better than the previous experiment. So I thought, well, I can try to do the experiment. And this is the experiment which I recently performed. So here, to make things even simpler, I just couple the cantilever directly to the squid. So this is the squid loop. It's complicated by the loop. And I bring the cantilever close to this squid. So the motion couples directly flux into this squid. And again, I see this thermal noise as a function of the frequency, which shows this Trenton peak. And again, I see that the temperature scale with the scale goes down by cooling down the system. Now, in this experiment, I had some complication compared to the previous because first, the quality factor now is changing with temperature, but before it was not. So it's more convenient actually to, instead of measuring the energy of the system, what I actually do, I measure this spectra and then I fit the term with this function, in which the Lorentzian term is basically this resonant term multiplied by this constant. And it turns out that this is just proportional to the force noise. Another complication is that, well, I have no time to go into detail, but there is some kind of cold damping. Yesterday I mentioned this. Basically, the quality factor is different from there is some effect, the squid influences the quality factor of this response, but by doing this fit, I just get rid of this, because I measure directly this coefficient, which yeah. Some? Yeah, there is actually good observation. Yeah, so there is another, here I try to make it simple as possible, but there is another term which is due to the squid noise. So the squid adds, now it is flat, but it's also add a small term which is asymmetrical. It's somehow resonance, anti-resonance. I didn't show here because it's a bit complicated, but I could measure this effect and characterize. It's just a small effect. It can see only at the smallest, at the lower temperature, but it actually it exists also here. You can detect it. And well, I can try to explain you. Basically, the SQUID has some noise, and we operate the SQUID in a feedback loop because that's the standard way to operate, to linearize the response. Therefore, you have some noise that flows into this. This noise has a current into the SQUID, and this couples back to the cantilever. And this mechanism has a transfer function, which is exactly this one. It generates a bit of, it's a very small effect, but it generates a bit of asymmetry. But sorry? No, in this case, there is no, you are very far from nonlinear effects. You mean the nonlinearity in the mechanical system? Yeah, no, you are far from nonlinear effects in the interior. This is just an effect of the SQUID noise. It's not a bending, it's just really that there is some noise that, well, you can show. So if this is the noise due to the external force, the thermal noise, that term gives a contribution which is something like this. It's a resonance and deresonance. So that here you see a lower noise with respect to here. That's what you see. But from the fit, in reality, the fit contains also this other term, which I didn't show here. And from the fit, you get the symmetrical part and this asymmetrical part. And we are interested in this symmetrical part. So this is what you expect from a noise coming from the mechanical system. So what I do here is exactly as before. I change the temperature. I measure the Q factor, I measure the temperature, and I measure this coefficient. And this coefficient should be, we expect to be proportional to the force noise of the cantilever, acting on the cantilever. And this is what I get. Basically, if I plot this as a function of the ratio T divided by Q, this is what I expect. A linear behavior. And this is exactly what I see. This is a very nice linear behavior. Which is the analog of the what I showed before for the other cantilever, which shows the partition result. The only difference is that in this case, actually, well, here I don't have an absolute calibration. That's one problem. But one can use actually this slope actually as a calibration of the thermal noise, as a calibration noise, to measure the coupling of the SQUID to this motion. The other thing is that, as you can see here, there is some, these are lowest point here. I zoomed in. As you can see, there is some extra noise here, some excess noise, which is definitely out of zero if you do a fit. The fit is linear, is good within the error bar, and I get that the intercept is off zero by 10 or 10, almost 10 sigma. It is definitely a finite effect. And so the point is, what is that? So, well, the most, the nicest solution would be that this is actually an application of CSL. That would be awesome. It would mean that we have finally discovered that quantum mechanics is wrong. But of course, that's not so easy to demonstrate. But the problem is that really I could not figure out what is the effect. So I tried to investigate some potential sources of this non-thermal noise. So the simplest is mechanical noise. So there is some vibration, some acoustical noise which fits into the system. This could be easily detected. However, I will show the next. I can also show immediately one. What I get, it's a bit, oh, sorry, I go through because I have too many. This is the next slide. So, well, I try to figure out what kind of thing can be this. So mechanical noise, it cannot be because I changed a lot. The main source of noise in the system, mechanical noise, it's by far is a compressor which is using this refrigerator. I can switch it on and off. And actually, the measurements are performed when this compressor is off. So you have this very nice and clean stuff. But if I switch on this compressor, the noise should increase by 2 or 3 orders of magnitude, the input mechanical noise. You have already seen many times, but since the experiment sits on a mechanically isolated stage, I expect a smaller effect. And in fact, if I switch on this compressor, I see some effect here, some bump, but essentially the peak is almost unaffected. And if mechanical noise were a problem, I would expect like 2 orders of magnitude increase. That means that the suspension, this isolation system I'm using, is working well. The guess is that this is not, it's very unlikely that vibration induced by this, by outside world are really a problem. I was actually more convinced that this was the solution, so some kind of detection noise from the SQUID. And in fact, if you do a calculation, the SQUID should have some kind of detection which leaks into the system, but it should be somehow some order of 10 times smaller than what I see. Then I did a simple test. I just increased the coupling of the particle, just to change the position. I increased the coupling by a factor of 3, and I repeated the measurement. And what I found is that basically I don't see any effect. So the point, the new point of this white point here, basically lie on the same line, the other data. I was very surprised with that, but it seems that the detection is not really a problem. Actually, this is consistent with the theory because the expected effect was like 10 times smaller. And I also tried to change the point, the working point, the parameter of the SQUID, but that didn't change significantly. And so at this point, I didn't know what to do. It's possible to figure out a lot of possible mechanisms. I tried to try magnetic field noise in the system, but it seems just too many orders of magnitude off from realistic numbers. So this is not a really experimental test. Just I did some considerations. It's possible that I see something as I showed in the other experiment, like the cantilever is getting warmer, but in that case, I would see, as I said before, I would see something like that. Linear behavior, which is getting to 0, and then saturation. Now I see really an intercept. So at that moment, I have no reasonable explanation, but well, that doesn't mean that there is no physical explanation, of course. There can be a lot. The first one, which one? This? Or this? This? Well, I did, these are 2 sets of different sets of measurement with different coupling from the SQUID to the cantilever, and this effect is basically the same. I would have expected a much larger effect, like 3 times larger, but I don't see it. This is the noise, well, it's a measurement of the noise from the fit, the amplitude of this peak. This is what you expect if you have no other effect. But in this case, I wanted to check if the SQUID has some influence, if there is some backaction noise from the SQUID. And to that, you increase the coupling, and therefore, by a factor of 3 roughly, and you would have expected this intercept to increase by a factor of 3. This is due to the effect. But I don't see this effect. Yeah, almost 10 to the 7. So, well, now there is some work to be done to understand this effect. Most likely, some could be something like this last option, but you have to play a bit with the model. I'm not sure if you get. Well, this is the coming back to your question. This is what you get for the CSL. So CSL, in principle, is a possible option. There is at least some parameter region where we are going below the previous experiment. Here we go much lower because everything is bigger here. So we are probing better this region and -5. But yeah, so if CSL is somewhere here, that we would not have seen this effect before. This effect could be in principle consistent with CSL. So that's nice. But okay. What? So this is just no, doesn't. Just the region which is around 10 to -7, which is more likely. In theory, it's like more, but there's no other. So this is the old experiment, and this is the new one. Yeah, it's exactly the same. Yeah, maybe yes. I don't know, below 10 -7. Actually, so the interesting thing is that, well, there is, of course, the nice option that this is something new or some CSL or so, but if you are able actually to remove this noise or to understand this excess noise, you would actually go down by more or less a factor of 10. This would be something like this. This would exclude more or less the other. So with this system, in principle, you can go. Okay, then maybe, yeah. So you mean less than 10 to -7. This one? You mean this? Yeah. You mean that it's just an artifact of the analysis that in reality you can go to 0? So you are asking if how robust is the analysis? The reason why these are larger. You're asking if you can go to 0. Oh, the second one. Oh, the error bar was very small here. Yeah, so, yeah, it's smaller. The error bar on this is actually smaller than this. I just put in as a guide. I didn't. Yeah, this is not without error bar, but is this measurement was actually more precise because I had more statistics, and I think this is more. Yeah, there is no error. No, there is error, but I didn't put here. But I think it was comparable with this. It's a bit smaller than the blue. But yeah, from the fit, I can give you the result of the fit. That good. This is just the old one. I show this just to facilitate the understanding, but maybe I made more confusion. But I did actually fit with the correct error bar with the green data. And what I get is that the intercept is actually slightly larger than the blue. But it's more or less consistent with the error bar. Yeah. The straight line is the blue one. I just superimpose the green data I just superimpose the green data. More? Yeah, the green, well, maybe. It's just accidental. No, but the red is the fit of the blue, yeah, because just superimposed. Other question? If you want, we can go further with a discussion in the afternoon. Maybe we can try to figure out other possible mechanisms to explain this effect, because it would be nice if there was CSL, but pretty much skeptical. If I have some time, I will just briefly describe the other way we have recently used to test CSL using gravitational wave detector. And you have considered different, in this paper, which is in the archive now, you have considered different possible experiments like macroscopic mechanical resonator gravitational detector, old style detector, LIGO, which you probably know how it works, and Ellis Pathfinder, which is a recently launched mission of ESA, European Space Agency, which is intended to, is a precursor of a future gravitational wave detector in space. Of like 1 million of kilometers of diameter of arm length. Here, everything is much easier because, well, the geometries are very clear and the effects are also easy to analyze. So basically, what you want to measure is the force noise, the effective force noise, which acts on the test masses of this interferometer, which is consistent with the measured spectrum. So basically, you're asking if there is some CSL acting on the mirrors of LIGO, what will be the signal you get in the actual spectrum, or the noise you get in the actual spectrum. And it turns out that this is very easy to do because this is the strain noise of the interferometer, which can be related with the spectral density of the displacement, very straightforward. Just the length of the arm length is the conversion factor. Then this displacement can be converted into a force because we have these masses and the free mass limit. In the free mass limit, the relation between displacement and force is just this mass times omega squared. So if you just take the spectrum If you have a constant white noise, like a CSL, test mass, it will appear as 1 over omega square noise in the strain spectrum. So if this is the measured spectrum, it will appear as a contribution which is this shape. So the best, what you can say is that assuming that we don't know, we are not able to completely know all the noise sources in LIGO, they know, but we assume that we don't. And in this point, you have the maximum. This line is 1 omega squared. So this is the point where the force noise is minimum in LIGO, and it's more or less something like 35 Hertz, I found, more or less. And you get something like 100 femtonewton per square meter noise. Now you can calculate using the formula that you can get from CSL model. You can compare this with the expected noise and as function of the parameters of the model. Then you can set an upper bound, exactly as we've done with the Cantilever. A similar thing you can do with this other experiment. This is a Pathfinder. What is this Pathfinder? This is essentially this very nice experiment in which also very simple conceptually. It's just two masses, test masses in space. This is a space experiment, and these are in free fall. So the idea is to measure how well you can have an object in free fall in space. And here they have a satellite around which protects the masses from solar wind and from any disturbances. And this satellite follows the masses. It measures the position of the masses, but then it tries to move around in such a way not to touch the masses. So the masses are protected and they are in free fall. And so there is a feedback mechanism based on microthruster, which the satellite has to continuously adjust its position in order to follow these masses. And then there is an optical measurement of the distance between the two masses which are nominally in free fall. And in this way, they measure the relative acceleration between two masses, which is like that. And this is actually without noise. And the system is optimizing to have very low acceleration noise in the range of the millihertz frequency, because this is intended to be a building block of a giant interferometer in space, where the test masses sit at 1 million kilometers or something like that distance. And you need, in order to use this to the gravitational wave, you need a free fall with the accuracy with this level, femtometer per square root. Femtometer per second square per square root of 5 is the acceleration noise. From this, you can calculate the force noise, residual force noise, which acts on a single mass in this environment. And what it turns out that this is actually better than LIGO because the material is denser, and actually the force noise is actually lower by 1 order of magnitude, more or less. And so it turns out that this is actually, this sets a way better limit on the first time. So what we have found is that, so this, this is the mechanical resonator, this is LIGO, and this is Pathfinder. This is compared with the Cantilever experiment. So now LISA Pathfinder is actually close to the Cantilever experiment sensitivity, which is quite surprising because the experiments are completely different. And this is a macroscopic experiment, so you expect there is a lot, you have a lot of many orders of magnitude which you lose in sensitivity because of the size and high temperature. But just because they work at a so low frequency and they don't have any kind of disturbance at this frequency, because you are in space, they achieve this remarkable result. And so this is remarkable. Of course, well, there is also a big gap in the cost of the two experiments. So you can do a cantilever experiment very easily with very simple stuff. While LISA Pathfinder costs like 1 billion of euros. So if you want to repeat the experiment, I suggest to take this one. This would be very difficult. They took 15 years or so of development to perform this experiment. And now it will take another 15 years or so to get to the LISA mission, which will be the gravitational wave detector in space. Space experiments, as you know, the time scale is this. Okay, these are the plot that's been shown already. I don't need to comment. It's just a zoom out of the previous one. Here, there is no yet this the last experiment with the cantilever. It will appear somehow. I think, well, I had some few slides about the fact that with the LISA and the gravitational wave detector, you can actually exclude a collapse model. This is the Ellis model. I don't know if Angelo described this, but it's just this is another collapse model which was proposed in literature, which comes from high energy physics, and it's very weird stuff like this is the coherence rather than a collapse, which will be caused by some bath of space-time wormholes or something like that. And the model is surprisingly, well, it's parameter-free, so you can just say this model is excluded because you plug in the data, the number, and you find that is excluded by many orders of magnitude. Actually, when we realized this, at the same time we realized that it just appeared on the archive paper which they demonstrated that matter wave interferometry also excludes the experiment. So it seems that this model is it's not true. Maybe there is some variation that can be survived. Another thing is that the Diosi-Penrose model, we define it RC, the single parameter model, which is similar to the CSL, but the intensity is big Z. Basically, you have some gravitational constant because it is assumed that gravity is the source of collapse. But then there is also RC, yeah, and using this LISA Pathfinder data, you can set a limit of this length of RC, like 10 to meter. It's probably not yet relevant for this model, but probably the strongest limit at the moment. No, this is not it. This is in this model. You mean on? Yeah. This is the this is the analog of the diffusion constant of CSL in the case of this model. Yeah, is this one? How much? This number, no, I don't remember. We can try to. I think, well, I'm going to then. Yes, you asked a question about cold atoms. There is another paper with an analysis of cold atoms experiment, like this one, which I did. They cooled a cloud of rubidium atoms down to picokelvin or hundreds of picokelvin or so, and they have very low heating rate, we have estimated, and from this you can actually get this video, which is, well, the shape is completely different, because basically you are in this part of the curve, and so you exclude, of course, the highest part above the line, and at 10 to minus 7, you are more or less in the same order of magnitude of the experiment. A bit worse, but The limit becomes worse at increasing RC, while it improves. If you compare with X-ray, it's way worse. But with this, Angelo did they analyzed other dissipative CSL model, which depends on the effective temperature of this CSL path. Okay, this is the end. I just conclude with just looking for the future, an outlook. With this kind of experiments based on conventional resonator, it's possible, probably it's possible to improve by 1 or 2 orders of magnitude by optimizing the parameters. This is not impossible. It should be quite possible. To go much beyond this is probably very difficult. For 2 reasons. One is that quantum limit becomes relevant at some point. The detection of this, already now we are close to seeing the detection, for instance. But the main reason is that you need to really improve strongly the quality factor, and it is very difficult. We have seen yet that with conventional resonator, you achieve this 10 to the 7, 10 to the 8, but it's very difficult to go. You know. Maybe it's possible to think about experiments micro-kelvin temperature, but that would be very difficult, of course. So probably with optical levitation or magnetic levitation, that's the only way you can really go well beyond this. And for instance, if you want to go down to the Girard-Weber original values, so that's also experiments in space are also promising, I think, because after there is a results, probably, well, experiments in space are very difficult, so you have to keep it simple, but in principle, you can achieve very good conditions for this kind of experiments. And of course, then you have to, the question if direct test with the matter wave interferometry can be actually go beyond this at some point. Now, this experiment with matter wave with direct effects are quite challenging, so I have no idea if the time scale, if one day it will be possible, or if it will be ever possible to improve over indirect test. In the sense that if you can reduce the coherence in a matter wave experiment to a level which allow you to go to a certain point, you will also have an environment where you have basically no external noise, so you could be able to see this with indirect effects. You could be able to achieve the same limit. That's just a question which I have no answer. Maybe somebody has. And okay, thank you for attention. This is the end of my lecture. Also, I think I have now far beyond.
Allowed parameter space is more tighter in CSL than other Colas models?
What?
These other Colas models like dissipative CSL and all, are the, allowed parameter range is more constant in CSL?
You mean this?
Compared to various Colas models, which one has the more tighter constant in parameter space?
You mean the Ellis Colas model?
So there is CSL and DCSL and GRW. So, among all these Colas models, which has most smaller allowed parameter space right now, according to experiments?
You mean this one? So, well, CSL basically, so you see that with the dissipative CSL, you have just that you cannot probe, so the probing region becomes, so in this case, yeah, by parameterizing, by setting the temperature, dissipative bath, you have different limits. A CSL is equivalent to a dissipative with infinite temperature, because the dissipative CSL, you have that. So in the standard CSL, you have just noise that comes, energy that comes from this CSL into your system. While in the dissipative CSL, they have developed in Trieste, there is, it's like a thermal bath, so you have both noise and dissipation. So there is also energy that leaks back from the system to
I mean, constants are stronger for CSL.
Here, it's stronger. CSL is stronger here because larger region.
Another thing is that I mean, the way we are excluding the exhausting the parameter space. I mean, how much sensitive it will be upon the details of the model. I mean, whether we consider CSL or some DCSL. I mean, will it be too much sensitive to the details of modeling, or
the details of the model?
I mean, what particular model you are choosing for the collage model? Will the allowed parameter range will be much sensitive to the details of the model or not?
I understand probably better if you don't use the. Sorry. Yep. Yeah. Yeah, well, I mean, you mean if I try to test this model using the Cantilever, for instance, or something like that? Other models like. In which experiment? Yeah, I understand what the questions. So you are asking if the. Yeah, depends. For this, it depends on the model. I think in this case, it will depend on the temperature of your measurement, also on what are you actually measuring. Because if you measure, like the experiment I showed, the initial one, where you measure the mean energy of the cantilever, then that is very dependent on the details because of the DCS. Because if the temperature of the CSL is higher than the temperature of your system, it's higher than you have just the heating. But if it's lower, actually with the cooling, there is nice to understand. You could even have a cooling of your system. But if you're actually looking at the force noise directly, like, I don't know, this is a Pathfinder experiment that direct measure the force without any. This is, I will guess this is more or less as strong as in any variation of the model. I don't know if this is the question. Yeah, I think you have to analyze, depending on the experiment, how much you are efficient in excluding the DCSL instead of the. But for instance, if you this collapse model with cutoff. Of course, it depends which frequency you are probing. So probably this Pathfinder is very strong because you are at very low frequencies. So you are safe in terms of the cutoff probably. While if you probe with some very high frequency system like X-ray, it's different. So it depends very much on the experiment.